Hello, this is Dr. Prasad Putilam with the YouTube channel My Intuition 4865. This is regarding the class series of Applied Physics for Computer Science and Engineering stream. Module 1 with laser and optical fiber, part 2 of module 1. And my classes are more oriented towards the application part, how it is useful for these topics, how it is useful for the computer science engineering students or generally the engineering students. Then the exam point of view, how you have to question answer type I am not giving, just explanation, detailed explanation and the practical implications of each and every topic, the meaning and all those things. So my YouTube channel, My Intuition, please do subscribe to my YouTube channel. That is the only support that I am expecting from you people. Subscribe, share my videos to others, and like. These are the these are the general expectations from a YouTuber. That too from a YouTuber who is taking class videos. Okay, now the point in the previous class I have explained on the first topic of module 1, explained about the characteristic properties of a laser beam and how the radiation interacts with matter. Now in part 2 I am explaining about the Einstein's A and B coefficient, then followed by the energy density and what is the importance of energy density. The derivation of the expression for energy density I am not giving here. Only how the Einstein's A and B coefficient are connected to the energy, how he derived. Actually, it's Planck's energy density. How Einstein further modified it with his effort. Okay, so the things goes back very long. How the Einstein started thinking about the A and B coefficient, which later end up in the laser and the fiber optic applications that we see in the as the module. Okay, so earlier the scientists were very curious. They were about thinking about how the objects they glow when they are heated. That we have seen when we heat an object, it will glow like the metal rod. First we heat a metal rod, it become reddish, then become orange, then it become white as it become hotter and hotter. So the scientists were worried, or they are thinking why it will glow in this way. So they had a formula to explain this, but those formulas were not working. This is called black body radiation. That is in 1900, a scientist, the Max Planck, he had an idea. He said that light is not a smooth. It is not. It is not flowing like a river. It is not like a as smooth as a river. It comes in tiny packets of energy called photons. Okay, so the Planck's idea worked well to explain the black body radiation, but there was still some more questions among the scientific community, that how do these photons they interact with atoms? How do the photons interact with the atoms? The Einstein's the big idea started. So Einstein started. He thought about this very carefully and came up with an answer during 1916. He explained how atoms and photons they work together. Okay, he said he 3 points he has given. It said that imagine an atom is calm and it is resting, that is in a very low energy state. So a photon with a right energy, it comes along. So the atom takes the photon's energy and jumps to a higher energy level, just like climbing up a ladder. So a calm resting atom, it absorbs the photon energy, then it climbs up a ladder, just means go to higher energy level. That is called absorption. Now the atom is in a high energy state. It does not want to stay there. Okay. Just like people, we go for a trekking, we climb a big hill, but we enjoy that moment, but we don't want to stay there. We come back, we want to come back. Okay, long time with high energy levels, it's not good. So it doesn't want to stay there, that whatever the energy absorbed. So after sometimes it releases that photon, and it goes back to its lower energy state. That is called spontaneous emission. There is another special one which is called stimulated emission. Again, Einstein said that what if another photon hits an excited atom. So instead of just passing by, the photon makes the atom release another photon. Now we have two identical photons. They have the same energy and moves in same direction, and that is how the laser works. Okay, so that is the balancing act. So the Einstein, he did not stopped explaining that. He further continued. Uh, he asked questions that if there are many atoms and photons in a room, how does this absorption, spontaneous emission, simultaneous emission, they balance each other? What is that balancing act between absorption, spontaneous emission, and the stimulated emission? So answer for him that he came up with the coefficient, the A coefficient called A coefficient, that is for spontaneous emission, and the B coefficient, that is for absorption, that is B12, and another B coefficient, that is for stimulated emissions. Now the A coefficient, that is called the spontaneous emission coefficient, it quantifies the probability of spontaneous emission, which is the process where an atom, after being excited, spontaneously emits a photon and transmits to a lower energy state. This is a unforced process, and the B coefficients, which is stimulated emission, and the absorption coefficients, uh, that is B12 for the stimulated absorption. This refers to the probability that an atom it absorbs a photon and jumps to a higher energy state when exposed to external radiation of the appropriate frequency. B21, that is for the stimulated emission, which refers to the probability that an atom in an excited state will be induced to return to a lower energy state by interacting with a photon. This is called stimulated by the presence of electromagnetic radiation of the same frequency. That is about the A and B coefficient of Einstein's. Now what are the applications of these A and B coefficients? Okay, now I understood what is A, what is B, B12 and B21. Now what is the applications of these? Not just for a idea which is generated in lab. It was an idea generated in lab only, but it has got a large applications. The scientists who are working the basic science, they introduced the idea, but the engineers took it to the next level, and still going further implementations are happening. That is the engineers' work. So they found that it has got, they derived or they developed the lasers. We have seen how the laser point, how it does it, or maybe the laser in movies during the surgery center. All these are possible because of the Einstein's idea of the stimulated emission. So in lasers, we need to make sure more atoms are in a high energy state than in a low energy state. This is called the population inversion. Okay, so the term population inversion I will be explaining the next class again in detail, but the atoms are in a high energy state done in low energy state which is created, that is called the population inversion. So using Einstein's coefficient, the scientists they figured out how to amplify the photons efficiently to create the intense or focused beam of light we call the laser. And today we have lasers as used in cutting welding material, used in medical surgeries. It is used in fiber optics, the internet cables, and the barcode scanners. Wherever we see in the barcode scanners, these are all the applications of lasers. The second application, that is spectroscopy. We know that the scientists, they identify different materials. New materials are developed, and how they identify those materials. The answer is the spectroscopy. Spectroscopy, it uses the Einstein's coefficient to study the light absorbed or light emitted by atoms or molecules. By analyzing this, we can understand the energy levels in atoms. We can identify the materials by their the unique way it absorbs or emits the radiations or the light patterns, which is called the spectra. Even we can detect the gases and even the pollutants present in the environments. These are the further applications of that spectroscopy, which is a continuation of Einstein's A and B coefficients. And astrophysics. Astrophysics means everything about the stars, sky. Einstein's coefficient also helped to understand this study about the stars, how the stars emit light and the heat because of the interaction between the atoms and photons, just like the Einstein explained. So in astrophysics, these coefficients are used to study the radioactive heating and cooling. Radioactive heating and cooling means how the energy moves through stars and the gases, as well as the stellar spectra. Stellar means the color of light from stars. It will, the colors which is coming from the stars will tell us about their temperature and composition. Just by observing what color the star is producing, we can we can guess approximately now almost accurately what is the temperature and what are the composition, what is the materials present in that star, as well as the cosmic phenomena like the black holes, and even more about the galaxies. Then comes the quantum electronics. Think about the optical fibers, the photo detectors, and the solar panels. All these devices, they work because of the interaction between the light and atoms, which is guided by the Einstein's ideas. So in quantum electronics, Einstein's coefficient are used to design the optical fibers which carry light signals over very long distances with very little loss, and it makes the photo detectors which convert light into electrical signals, or it is used to build the solar panels which capture sunlight and turn into electricity. Therefore, the Einstein's A and B coefficient, uh, they just started as an idea to explain how the light and the atoms they interact, or how they behave. It helped us to build the lasers which power the industries, the spectroscopy to study the materials and gases, to understand about the stars, to understand about the universe, to all about astrophysics, as well as creating an advanced optical devices used in the present quantum electronics. Now, how it can be further connected to the density of energy density. The balance of absorption, the spontaneous emission and the stimulated emission, it rates give us the following relationship given in the slide. Yeah, U equal to the energy density equal to A21 divided by B12 e to the power H nu K ABT minus B21, where A21 it is the probability of the spontaneous emission, which is independent of the energy density. B12 is the rate of absorption, which is proportional to the energy density. B21 is the rate of stimulated emission, which is proportional to the energy density. So Einstein showed that uh, to satisfy the Planck's law, the coefficient must be related as B12 equal to B21. That is, absorption and stimulated emissions have the same energy density. Okay, that I have given here. Okay, B12 and B21, they are equal, absorption and stimulated emissions have the same dependence on the energy density, and the A21 divided by B21, which is equal to 8 pi h nu cube divided by c cube, which relates the spontaneous emission to the stimulated process. So by substituting this the relationship between the Einstein's coefficients A and B into the rate equations and solving for the energy density, Einstein derived the same form of energy density as Planck's law or Planck's equation for energy density. That is given here, where h is the Planck's constant, c is the speed of light, k is Boltzmann's constant, T is the temperature of radiation. So this formula describes the black body radiation, which is the spectrum of radiation emitted by an idealized object which absorbs all incident radiation, which is called as the black body. The energy density, it is proportional to the temperature to the fourth power. That is actually Stefan Boltzmann's law, and the energy density is proportional to the frequency of radiation. So thus Einstein's coefficients provide the quantum mechanical explanation for how energy density arises from atomic interactions with the radiation. So these Einstein coefficients, they bridge the gap between the quantum transitions in atoms and the macroscopic energy density of radiation, which is described by Planck's law. Now we will see the applications of the energy density or the equation expression. It can be used to understand the radiations in stars. I explained already the energy density of the radiation in star. It helps to determine their temperature and the emission characteristics, what type of materials present in the stars. In astrophysics, knowing the energy density of the radiation emitted by the star, it is very crucial, very interesting to understand the life cycle and the interaction with the surrounding environments. Then the second point, that is laser designs. In a laser system, understanding the energy density, it helps in the design of the laser cavity, where the radiation intensity, it is optimized for maximum output. Majorly for the designing of a laser, it is very much useful, the energy density. Then comes the thermal radiation. the expression given for the energy density, it make us to a scientist to design, engineer to design the thermal devices like the thermal cameras, the infrared sensors, the heat exchangers. So these are the devices which are developed by the engineers, which relies on or which are depending on the understanding of how the energy is radiated from the hot surfaces. Oh yeah, that's about today's topic on part 2. Hope it was useful. I have not gone for deriving the expression, which is a major part of the syllabus, deriving the energy density equation. I just given only the introduction and the application, how it was connected from Einstein's A B coefficient to the energy density, and how it been useful, how the engineers made use of those. So that part is very important. I felt very important. How the engineers are taking it up, that an engineering aspirant or the student of engineering should understand what is the importance, why it is there in the syllabus. Hope it was useful, meaningful. Then please do subscribe to my YouTube channel, my intuition 4865. Please do share this video to your friends. Please uh, do like my videos and support me in that sense. So once again, thank you very much for watching my video. Have a nice day.